All right. So we're going to keep working on shear and moment diagrams a little bit. Our midterm is going to be Monday, okay? And it will just cover through Chapter 7. So we're not going to start on Chapter 8 until after the midterm, all right? Chapter 7 is shear and moment diagrams. That's it. So is it from Chapter 1 through Chapter 7? I mean, yeah, but we're focusing on the recent stuff, okay? So my plan is today we're going to finish Chapter 7 mostly, okay? So there's the graphical method of doing shear and moment diagrams. And then on Friday, I'll be happy to answer questions. We can do review of if there are areas that you'd like to review. So if there's areas you've struggled in, shoot me an email and I'll make sure and go over those on Friday. And then we'll have our exam on Monday, okay? And then we'll start Chapter 8 a week from today, okay? So let's go ahead and talk through this a little bit. Does anyone notice anything about if you compare the forces that are acting on this and the shear diagram, do you see any similarities? Where the forces are applied, there are changes, absolutely. How does it change where the forces are applied? Same amount as the force, right? There's a jump up or down that's the same as the force. So you'll notice we start at 0 here, and there's an 8 kilonewton upward force at A. And look at that. The graph jumps up 8. Nothing happens as we go from A to the 6 kilonewton force, so nothing happens in my shear diagram. When I hit that 6 kilonewton force, I jump down 6, right? Because now I'm at 2. Then as I go from 6 to 12, nothing happens. When I hit 12, I jump down from 2 to negative 10, or 12, right? I jump down 12. Nothing happens from the 12 until I get over to B, where there's a 10 kilonewton force going up, and I jump back to the abscissa. Right? So without doing any equations, we actually could come up with this graphically. And that's kind of what we're going to talk about today, is the graphical method for doing this. Let's go a step further, though. Do you notice any relationship between the shear and the moment diagrams? It's the derivative. What do you mean it's the derivative? Your slope changes based on the value of the shear. In fact, the slope right here, right? We go 16 horizontal for going up 2. What's that mean the slope is? 8. What's the value of the shear diagram here? 8. Okay? Here, our slope is, we go oh crap, I did this backwards, guys. I'm sorry. We went 2 meters and up 16, right? Here we go up 4 in 2 meters. So what's my slope there? Huh. Okay. What do you think this slope's going to be? Negative 10. Right? Because here we go 2 meters and down 20. So it's a negative 10 slope. Okay? And we can actually go through and develop kind of a set of equations for this. And let's start with doing the ones that relate the shear diagram to the moment diagram. So a little bit backwards. We'll start at the end and work our way towards the beginning. Okay? So we're saying that the value of the shear diagram, V, is equal to what? It's equal, somebody said it. The slope of what? Of the moment diagram. Okay, so this is value of shear gives us slope of moment. Okay. Now, this is sort of related, but as we go from A over to the 6 kilonewton force, what's our change in moment diagram? We go from 0 to 16, right? That's the area underneath the shear diagram. So we could say that the change in the moment is equal to the integral of the shear. Right? Because this is 2 meters. So the area underneath this is 8 times 2, or 16. Holy smokes, we changed 16. It even works over here where we have area below. So we go 2 meters here, but it's at -10. So we have a change of 2 times -10, or -20. And wouldn't you know it, we go from 20 to 0. That is dx. Yes, that is dx. Right? So this says the change in moment is equal to the area under shear. Okay? Now, what's the slope of this line? Okay? I'm going to give you another one. The okay? This is the magnitude of distributed load gives you the slope of the shear diagram. And the change in the shear is equal to the integral of the load curve. Or the area under the load curve. Okay. So how do we apply this carefully? We apply it very, very carefully. Let's try some examples. Okay. Let's solve for our reactions first. Let's do that by summing the moments about A and setting them equal to 0. Here's A, here's B. Okay. So it looks like I'd have minus 10 times 3 plus 2 times 6 plus by times 9 equals 0. Right? So negative 30 plus 18, excuse me, negative 30 plus 12, it's negative 18, right? Plus by times 9 equals 0. So we take that to the other side. It looks like by is going to be 2. That means that ay is equal to what? 6. Okay. Everyone good with that? Okay. So now, I take my graphical approach to shear. If I have an arrow that points up, I jump up that much. So I'm going to jump up to 6 right off the bat. I'm going to come across. I'm going to jump down 10. Negative 4. Come across. Jump up 2. Keep coming across and jump up 2 more. And I have a shear diagram. Okay? Now let's see if we can get the moment diagram from this. What's the slope of my moment diagram going to be? It'll be 6, right? Because the slope of the moment diagram is the value of the shear diagram. Okay, so that means I'm going to do something like this. What's my change? I go across 3, so it's the area underneath this, which is 6 times 3, 18. Okay. Now what's my slope become? Negative 4. I'm going to slope down for 3. So if my change, to figure that out, we know I go 3 at negative 4, so I have a change of negative 12. So I know I'm going to end up at 6. How do I know I end up at 6? Because I know this is a value of negative 12 right here. This had positive 18. So 18 and negative 12 gives me 6. Now what happens to my slope? Steeper or shallower? Shallower. Okay. The change would be 3 times 2, negative 6. Look at that. We end up at 0. I now have a moment diagram.
In real life, is there like a program for this?
Oh, so the question is, in real life, is there a program for this? Heck yeah. Absolutely. Yep. Yeah. I'll show you output of that, and I'm going to give you a problem to work, and while you work it, I'll go look up something in my email for you. Okay? Okay, so go ahead and solve this guy. I'll pause it. Go ahead and solve that. Come up with a shear moment diagram as you go across it. Label it how, yeah, whatever. So I'll interrupt while you're doing that. We can look at my awesome phone here. Get some focus. Focus. Okay. So this is a retaining wall design I was having done for some people that are building a shop. So there's a big footing that goes in the ground, and then this is a concrete wall that goes up, and you can see there's a slope of soil behind it, right? So there's a shop floor here, and then they're digging this kind of the foundation into a hill. And so there's a slope that comes down. So this is acting, this is acting like a giant cantilevered beam, right? So if you look at this, there's a force loading it that's trying to make it tip over. And so what the designer has to do is come up with what the bending moment is on that as you go on the wall as you go through it. And so it's showing that the bending moment, actually, what's that say? Apply. This is the applied shear diagram, it says. So that's the shear on it. And here's the applied moment diagram. Okay, so shear and moment showing what, and again, in this case, the beam is standing straight up and down instead of being horizontal, right? So this is, I don't know what this program is, but every engineer I've ever had do some sort of retaining wall design has used this program. The output looks always exactly the same, so I don't know what it is, but there you have it. Okay, and it does a bunch of calcs and tells you kind of what that final output is, and this is where you have to stamp it, because this is a professional engineer, okay? Nope, that's Mia Mahidi's stamp. Okay? I could stamp it, but I don't feel comfortable stamping it because I don't do this every day. So that's part of being a professional engineer is knowing your limits. So my limit is I don't do it every day, so hire someone that does. I teach every day, absolutely. I'll put my stamp on that. You want me to bring a stamp in? I'll put it on you. So what'd you get for reactions? 4 kilonewtons here, 8 kilonewtons here. Okay. So then I can draw my shear diagram. I jump up 4, it looks like. Jump down 10 to negative 6. Jump up 8 to 2. Jump down 2 back to the axes. Okay. So the question is, does it ever not end at 0? And the answer would be, when you have a purely cantilevered beam, you're going to jump up at the very beginning, right? So it doesn't really necessarily end at 0. Yeah. But if you think about it, what we're plotting here is an internal shear force. So you can't have an internal shear force that's not 0 at the end, right? Because there's nothing happening at the end, or it's accelerating. Yep. Okay. So moment then, positive change, 4 times 3, we go up to 12. Bloop. Negative change, negative 6 times 3 is negative 18. So we're going to come down to 6. Bloop. Positive change, 3 times 2, or 6. Bloop. Right? Looks something like that. What's that? You love this method? Ah, but wait. There's more. Okay? Okay? Go ahead and find me the reactions for this bad boy. What do we get for reactions? Here, 9.17 and 15.8. Hopefully 0.83. Okay. So we can do our shear diagram then. Boop. Boop. Jump up 9.17. Boop. Come across, jump down 10 to negative 0.8. Right? No change till I get to here. Uh-oh. Now what do I do? This is discouraging. Do I jump down 15 all at once? Nope. Remember, if we go back to these equations, it works the same. The way these two are related is the same. This is related to that. So the change in my curve as I go from here to the end is going to be the area underneath this guy. So 3 times 5 is 15. So I know that I'm going to end up 15 below this. Okay, so I know I'm at negative 0.8 here. So that means I'm going to end up at negative 15.8. Okay, the slope at which I do that is the magnitude of the load curve, or negative 5. Okay, that should be a straight line. It's a little bit of a curve. I'm going to fix it by making it fatter. Okay. And then I jump up 15.8. That line right there is a straight line. I'm sorry. I'm a terrible person. All right. Okay. So how do I do? This is still related the same way, right? So I know the slope of my moment diagram as I go across here. It's 9.17 times 3. 27.56. 27.51. Such a disappointment. Stanford called, they want their degree back. Ouch! Okay. As I go from here to there, then it's going to be 0.8 times 3, so 2.4 down. Slight negative slope. Still a straight line. Okay. So 0.8 times 3 is 2.4, so I'm going to be at like what, 25? 25.1. Okay. Then I have this guy. Well, holy smokes. Okay, a couple things I want you to look at this. We know that this, the shear, gives you the slope of the moment diagram. So we know we start a little negative. In fact, we start tangent to the line here, right? And it's increasingly negative. So tangent, but increasingly negative, right? What's the total change? Well, I could figure that out if I wanted to. I have a triangle here that has a height of 15 and a run of 3, right? So the total area there would be 45 over 2, or 22.5. And then I have a rectangle here that's 0.8 times 3, or 2.4. So 2.4 and 22.5 is really close to 25.1. Okay? So here would be my moment diagram. This curve? Well, all I did is that I knew its endpoint, right? I knew the change that we would have, and I knew that it's a negative slope, increasingly negative. And so this is just it's increasingly negative and it goes to 0. Right? That's good enough for me, but it's going to get a little trickier. Do you have an idea how you could figure out what the equation of that curve is? Yeah, so the response was you could take the integral of it. You certainly could, or you could just draw the beam, right? Sorry. It's like I've been drinking before I came to class or something. Geez, can't draw straight for nothing today. Okay, so I could draw the beam, 9.17, 10, some part of the distributed load, shear, and moment, right? And solve for m. It will give you the equation of this line. So you can go back to the method before that we were using. We'll give you the equation of that line, right? Okay. So everyone still likes this method, okay, right? Still pretty easy. Just wait. Just wait. I got my snowplow home the other day. Pretty excited about it. I don't know. I bought a snowplow the other day. Did I not tell you I bought a snowplow? Oh, yes. My equipment junkie ways have manifested themselves again. Couldn't help myself. Yep. Had to buy me a snowplow truck. Nope. I do. It is an expensive habit. I will say, though, that I almost always sell my habit indulgences for more than I buy them for, so it works out.
I respect the hustle.
Thank you. Thank you for respecting the hustle. It is my side hustle. No, so I bought the snowplow because remember last year Seattle got like a week of snow and it like shut down the whole city?
I don't remember.
And some guy, like some 18-year-old kid from Idaho, was visiting his mom in the hospital there. And he saw all the snow, so he went back to Idaho and he got his plow truck and he came back to Seattle and he made like 30 grand in a week. And I thought to myself, typically when it snows, I don't have to work, right? So it'd be a perfect side hustle to have a snowplow for the 1 week a year we get snow. It's a good side hustle, I tell you. All right, so we're going to say that there is a 30 kilonewton per meter triangular distributed load on this, okay? And I'm going to say that this is 9 meters long, all right? So we know that there's 9 times 3 is 270 divided by 2 would be 135 kilonewtons acting right there, right? Then we'd have to 1/3, 2/3 that to figure out our reactions. So could someone tell me what 2/3 of 135 kilonewtons is? Okay, so there are my reactions. Finding the reactions, if you're worried about it, go ahead and do the math to figure them out on your own, but those are the reactions. Okay, it's not what we're worried about right now. So it's time to come and do my shear diagram for this bad boy. Okay, I know I jump up 45. Bada bing, here I am at 45. Then what happens? What's my distributed load doing? Down, right? So remember that the shear is the slope. No, wait. wait. How much change will I have as I go across? 135, right? So I'm going to go from 45 to negative 90, right? And my slope is going from 0 to negative 30, right? Because the slope of the shear diagram is the value of the distributed load diagram, right? The slope of the shear diagram is the value of the distributed load. Okay, so that means that I've got something that looks like okay, and then it jumps up. Okay, it's increasingly negative. Negative and increasingly negative. Yeah? Everybody good with that? Now what do we do? Oh, man.
What is the value all the way down there?
This is going to be negative 90, right? Because remember I said my change had to be negative 135. So I go from 45 minus 135 is going to get me to negative 90. Which works out well since I have a 90 jump up then, and I'm back to 0. I hear a little murmur. Oh, this is going to be a cubic function. This is not so pretty anymore, right? But let's see if we can make our chart, okay, let's see if we can make our chart work. What do we know about the slope of the moment diagram right here at 0? What is it? Nope. The slope of the moment diagram right here, what is it going to be? 45, right? Because the slope of the moment diagram is always, you could think of the shear diagram as being the plot of the slope of the moment diagram, right? So, oh, that means it's 45 right there. Pretty steep. Okay? Positive 45 as well. What's the slope here? Negative 90. Super steep. Maybe I'll make this one a little bit more like at 45. Yeah. What's the slope of it right here? 0. So we're going to hit a flat spot right there. Is the slope increasingly positive or decreasingly positive? Decreasingly positive. So it looks something like this. Increasingly negative. Right? That is what the thing looks like. Does this tell me anything that I need to know? It tells me the shape. But it doesn't tell me the magnitude here. Does it tell me where this is at? Does it? I mean, we don't know where this is, right? We just kind of went, well, it's negative, increasingly negative, right? So no, we don't know. Is this important? You bet, because we know, okay, right there is my max bending moment. So now how do we find that? Not great, right? I don't have a great way to do this. We have to actually like work now, right? Like before we were just drawing pretty pictures. It was like paint by number before. But when you get a triangular load, and heaven forbid that the reality is that snow doesn't pile like that, right? How does snow actually pile? Probably something like this, you know, some curve thing. Oh, man. Now we're really in trouble, right? This is why engineers see the world as triangles, okay? Because we don't like doing math. right? Okay, so how could we solve this? Well, gosh, this is where we have to go back to our original method, right? This graphical method, this works great when we're dealing with just point load forces, or when we're dealing with very simple rectangular loads, right? And this is the majority of engineering, right? The majority of engineering is we have a distributed load. If you think of a pool, right? Hydrostatic pressure, distributed load. Any pressure, typically that's just a distributed load, like a pressure over an area, okay? So pretty unusual that we're going to end up with something like this. When do we end up with this? No, no. When we're looking at, like that beam I showed you on my phone, a dam, right? If this is a dam and there's water behind it, it turns out that pressure does this, right? Pressure gets more as you go down, has zero pressure at the top. You experience this when you play dead on the bottom of the pool and try and freak your parents out, right? Your ears hurt, okay? And as you come up, they hurt less. That's because the pressure changes as you go down, right? So in this case, okay, this is a common engineering problem, okay? And so you would have to solve it this harder way. But we'll go back. We can still deal with this, right? We just have to solve it by saying we have 45 kilonewtons up here. We have a distributed load, right? And this is some distance x. Shear is still down. Moment is still counterclockwise. What do I put on this right here? What do I put on this for the magnitude right here? Right, because I'm slicing the beam. Say I'm going to slice it right here. Right? So I need to figure out what's the magnitude of the distributed load at that point so that I can put it on right here. One half of 30x? No. So the distributed load is going from 0 to 30, right? This is the magnitude. This isn't the equation of the line. This is the magnitude at the right-hand side. So we have a rise of 30 with a run of 9, right? So this would be 30/9 x, right? Because if I'm at 9, it'll be 30. If I'm halfway across, right, if I'm at 4.5, it'd be 15, right? You guys picking up what I'm laying down here? So I'm just looking, I need to find the slope of this line, and then I know that the magnitude here would be 30/9, because that's the slope, 30 divided by 9 times x. So just take the magnitude at the right-hand side and divide it by the length over which it happens, okay? So 30/9 x. And now we can go about solving this like we would before, where we would say, all right, sum of the forces in the y has to equal 0. So I'll have 45 kilonewtons up minus, well, how much of this acts down? Oh, geez. What's the height of the triangle? Well, the height of the triangle would be 30/9 times x, right? That's the height. What's the base of the triangle? X, okay? And we just want, so we're doing our, like, we know we're breaking this into a resultant, right? And that whole thing would have to be divided by 2, right? Because it's not rectangular. It's a triangle. Okay, so we're finding the area underneath this distributed load is going to be the base x times the height, which is 39ths x. Right? Yep, because for the whole triangle, that's okay, the whole triangle, so the question is, where does the 39ths come from? The whole triangle goes from 0 to 30, so it has a rise of 30 over a run of 9. So the slope of this line is 39ths. Okay, so all we're saying here is that on this similar but smaller triangle, the slope of the line is going to be the same, 39ths. The peak, this top point, would be times x. Okay, so then I need the height times base of my triangle times 1/2, right? So 39ths x gives me my height times my base x divided by 2. All that plus v, minus v equals 0. So we get v is equal to 45 kilonewtons. Oh gosh. Minus 39ths divided by 2 would be 30/18ths x squared. (30/18ths) I think is 5/3, but whatever. Okay, so this just gave us the equation of this here line, right? I want to know, where does it cross the 0 point? Well, I can say, okay, well, where is the shear equal to 0? So I say, okay, 0 is equal to 45 minus 5/3 x squared, or 45 times 3/5 is equal to x squared. Let's see, 45 divided by 5 is 9. 9 times 3 is 27, is equal to x squared. So it looks like x is equal to plus or minus 5.1. What is it? $5.2. Okay, so we know this is at 5.2 meters. Okay, that's where our maximum bending moment is, and it's where our shear force is equal to 0 inside of the beam. Oh boy. Now we have to go find what that moment is. 2 ways we could do it at this point. Brendan just said one. I could take the integral, right, of this from what? 0 to 5.2. So let's do that. Let's take the integral from 0 to 5.2 of 45 minus 5/3 x squared dx. So that looks to me like it's going to be 45x minus 5/9 x cubed. Is that right? 3/3. Yep. Evaluated 0 to 5.2. And so what am I doing here? I'm finding the area, right? I'm finding this area here. Doot, 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 doot. Okay. Anybody give me a value for that? Wait, let me guess. 45 times 5 is going to be like 250. That cubed is 125, and you're looking at a little over half of that, so 75. I'm guessing 177. Dang it. 155.9. Okay. And that would be kilonewton meters. Okay. You got this? How else could I have done this? I could have done it the old way again, right? So I could have said, I could have looked at this free body diagram and said the sum of the moments about the cut is equal to 0. Right? Okay, so the sum of the moments about the cut is equal to 0. So let's see, I'm going to have negative 45 times x, right? Plus, 30 over 9x times x divided by 2, that's finding the magnitude of this, times x over 3 plus m equals 0. What does this look like? Let's see, we're going to end up with m is equal to 45x minus, let's see, that's x cubed, 30x cubed, divided by 6 times 9 is 54. Is that right? Yeah, where did I get the x divided by 3? This is the force. Remember, a moment is a force times a distance. And in this case, the force is the area underneath this. So it's the length, or excuse me, this is the height times the length divided by 2. So the x over 3 is the fact that this is 1/3, 2/3, right? So it's 1/3 x away from the cut, right? So 30 over 54x cubed, m is equal to 45x minus, let's simplify this, divide by 6, I get 5/9 x cubed. Hot dang, that's the exact same thing as right here. Look at that. Math works. Even a fool like me could get this to work, right? So math is crazy. All right. We'll go over some more of these on Friday. Again, the exam is going to be on Monday, and we'll cover through using this method. Okay? Through 7-3. All right.